Welcome back to the Science Hub SKB with Miss B. Sound waves, part 1. The objectives of part 1 would be to find out what is sound, learn about sound propagation, explore pitch and loudness, and identify ultrasound and infrasound. What is sound? Sound is a form of energy. It is produced when an object vibrates. These vibrations create longitudinal waves that travel through a medium like air, water, or solids and can be detected by our ears. Sound propagation. Sound cannot travel or propagate through a vacuum like light can. Sound waves can only travel through a material medium such as air. Hence, sound requires matter in order to travel. Sound waves are produced by mechanical vibrations. Types of waves. A transverse wave has vibrations perpendicular to its direction of propagation, while a longitudinal wave is one that has vibrations parallel to its direction of propagation. A spring can be used to produce a longitudinal wave. When a spring is pushed in a back and forth motion, compressions C, where the coils are close together, and rarefactions R, where the coils are farther apart, travel along the spring. In a longitudinal wave, the particles of the transmitting medium vibrate to and fro along the same line as that in which the wave is traveling, not at right angles to it as in a transverse wave. Sound travels as a progressive longitudinal wave. Sound gives interference and diffraction effects and is often believed to be a form of energy because of that. A longitudinal wave can be sent along a spring. In summary, sound is a longitudinal wave and it requires matter to travel. Comprehension. Read the statements and say whether they are true or false. Sound is a form of energy. Sound, like light, can travel in a vacuum. Radio waves and thunder are both examples of longitudinal waves. Sound cannot be heard in space. A crest is to a compression as a trough is to a rarefaction. Yay! Did you get it right? Good job! Exploring pitch and loudness. Parts of a transverse wave can be compared to those of a longitudinal wave. This is because sound waves, although longitudinal in nature, can be displayed on an oscilloscope as if they were transverse. The oscilloscope is a machine that interprets the changes in air pressure of the sound wave and generates a visual representation. From this, we can observe features such as crests and troughs, allowing us to investigate the wave's amplitude and wavelength. The crest is the highest point of a transverse wave. It represents the maximum upward displacement of the wave's resting position. The trough is the lowest point of a transverse wave. It shows the maximum downward displacement from the resting position. The wavelength is the distance between two identical points on a wave, such as from crest to crest or trough to trough. It tells us how long one full wave is. The amplitude is the maximum displacement a wave moves from its resting or undisturbed position. It tells us how strong or loud a wave is. Bigger amplitude equals more energy. In longitudinal waves, a crest is to a compression, as is a trough to a rarefaction. A wave of greater frequency produces a sound of higher pitch. Frequency is the number of vibrations occurring in 1 second. A vibration refers to a full wave or wavelength. The SI unit of frequency is the hertz, which is equivalent to a per second. A greater amplitude wave gives a higher or louder volume. Sound intensity or loudness is determined by the amount of energy that sound waves carry. A loud sound has a high sound intensity, while a soft sound has a low sound intensity. The SI unit for sound intensity is watts per meter squared. Another unit of sound intensity is decibels, where 0 decibels is equivalent to 10 to the negative 12 watts per meter squared. The safe sound intensity for the human ear is 85 decibels. Identifying ultrasound and infrasound. Frequencies below 20 Hz is referred to as infrasound. The human audible range for hearing is between 20 Hz to 20,000 Hz. Frequencies above 20,000 Hz are referred to as ultrasound. As one gets older, the upper limit gradually reduces to about 16,000 Hz. Uses of ultrasound. 1. Medicine. Also known as diagnostic imaging, ultrasound is used to view babies inside of the womb. It is also used to examine internal organs. 2. Communication. Animals such as dolphins use ultrasound to communicate with each other. 3. Measuring distance. A. Depth sounding is the use of ultrasound by boat operators to determine the depth of an ocean floor based on the time it takes the ultrasound to reflect. Since the sound wave travels twice, then to find the distance of the bat from its prey or the boat from the ocean floor, the following equation may be used, where S is equal to 2D over T, where S means speed of sound in meters per second, D means distance in meters, and T means time in seconds. B. Bats are nocturnal creatures. To navigate and judge distances in the dark, they emit ultrasound waves that bounce off objects. By analyzing the echoes, bats can determine how far away these objects are. Fun facts about bats. The phrase blind as a bat is a myth. In fact, most bats have good eyesight, especially fruit bats, also known as flying foxes, which can see quite well in daylight and at night. Many insect-eating bats use echolocation, a type of biological sonar, to navigate in complete darkness. But that doesn't mean they're blind. They use both sight and echolocation depending on the situation. So while they rely heavily on echolocation to hunt and fly at night, their eyes do work. Some species even have excellent night vision. In summary, the pitch of a sound is dependent on frequency. The loudness of sound is dependent on the amplitude of a wave. The human audible range is 20 to 20,000 Hz. Ultrasound is anything beyond 20,000 Hz, while infrasound is sound that is lower than 20 Hz. And most bats have great eyesight. Label the following parts, A and B, of the sound wave. Correct. A is the compression and B is the rarefaction. Comprehension. Fill in the blanks with the appropriate words. The pitch of a sound refers to its dash. The higher the pitch, the dash the wavelength. The dash of a sound is dependent on its amplitude. A low sound has a dash amplitude. Birds usually sing with high dash when compared to the growl of a bear. Awesome sauce, did you get them correct? The pitch of a sound refers to its frequency. The higher the pitch, the shorter the wavelength. The loudness of a sound is dependent on its amplitude. A low sound has a small amplitude. Birds usually sing with high frequency when compared to the growl of a bear. Comprehension. What is the unit for sound? What is the SI unit for frequency? What is the human audible range? What is ultrasound? What is infrasound? The unit for sound is decibel. The unit for frequency is hertz. The human audible range is 20 to 20,000 hertz. Ultrasound is any sound that is greater than 20,000 hertz, while infrasound is any sound that is less than 20 hertz. Based on the information in the table, which animals can hear ultrasound? Based on the information on bats, fur seals, beluga whales, sea lions, harp seals, harbor porpoises, bottlenose dolphins, porpoises, dogs, cats, rats, opossums, and horses can hear ultrasound. Comprehension. What are some uses of ultrasound? And a sonar ship receives a sound wave 5 seconds after it is sent out. If the speed of sound in water is 1500 meters per second, how deep is the ocean floor? Use S equals to 2D over T. Remember, S represents the speed of the wave, D the distance the wave would have traveled, and T the time. Answer. What are some uses of ultrasound? Diagnostic imaging in medicine. Ultrasound is used to view a fetus during pregnancy or to examine internal organs like the heart, liver, and the kidneys. Animal communication. Dolphins use ultrasound to communicate with each other. And navigation and hunting. Bats use ultrasound or echolocation to navigate in the dark and to locate prey. Answers. First, I always tell students to list what you have. So S is equal to speed of sound wave 1500 meters per second. The time is 5 seconds and the distance is what we're looking for. If S is equal to 2 times the distance divided by the time, then we can transpose for D, where D will be equal to the speed of the wave times time divided by 2. Hence, if we multiply 1500 meters per second by 5 seconds and divide by 2, we get 3,750 meters. The ocean floor is 3,750 meters deep. Okay, and the reason why we divide by 2 is simply because the sound wave makes the distance twice. It travels to the floor and back. So we want to get the actual distance of the ocean floor by dividing the distance that the sound wave actually traveled by 2. Thanks for joining me on the sound waves part 1.